This should not take a long time. So, the quadratics that you guys have been working with at this point in time are in what we call standard form. I haven't really addressed that because I didn't think it was important yet, but the ones that look like this, no, number times x squared plus number times x plus number. That's all I've been giving you so far, where we do the negative b over 2a. That's called standard form, just FYI. So today, we're not going to do much math, just graphing. Starting on Monday, then, and I don't know, maybe it's time for a quiz. I don't know yet, but the next step in this is to teach you how to convert standard form into vertex form. Because graphing in vertex form, as you'll see today, is one of the easiest things that I'll teach you all year. So the takeaway from it is we say, gosh, why can't all quadratics be standard form? And the reality of the situation is that a lot of times we can make them into vertex form. So like if I give you a standard form and you say, gosh, I wish it was that other one, a lot of times we can actually change one into the other, and it's not really all that hard. So it all kind of comes together starting probably Monday. But anyways, the old one, the one you maybe you're still working on, I don't know, is called standard form. So today we're going to do vertex form. And vertex form, the the general form of it, we say, like, how there's like y equals mx plus b. That's a general form of a slope-intercept equation. Y equals ax squared plus bx plus c, like you just saw, is the general form for a standard form quadratic. The general form for vertex form is a times x minus h squared plus k. And those letters, honestly, I was thinking about it this morning, and they're arbitrary. Like H and K don't have any significance. I mean, they can be. I thought about changing K to V for reasons you'll soon understand. But anyways, this is what you would see like in a textbook. This is what people would say. Okay, there it is. That's the general vertex form of a quadratic equation. Boom, just like that. So the numbers have jobs. You've seen this with it's a little bit more clear with vertex form, but like every number always has like a specific purpose or a specific role. A, we know, is the builder, just like he's always been, right? That number A has always been the one that tells us, like, do I go out one, up one, or do I go like out one and down two? That number's always been the guy that tells us like what to do once we get to the build site. H, conveniently, is our horizontal shift. And K is our, want to guess? Vertical shift, which is why I was thinking this morning, maybe I should just rewrite it, rewrite math history and call it a times x minus h squared plus v. And then at least h stands for horizontal and v stands for vertical. But anyways, I didn't want to do that because then some professor someday might look at you like you got two heads. Do you mean K, not V? So anyways, the numbers each have roles to serve. So again, A tells us how to build, H tells us horizontally which way to shift, and K tells us which way vertically to shift. The flow of this is exactly the same as it is with standard form. Like you want to find the vertex. That's job one. And then once you get the vertex, you disregard everything in the equation except for A. A is the only number that winds up mattering because he tells us just once you get there, build it like this. And you don't have to do any math, which again, I know for some of us is really good news because not all of us love math. So this is what it looks like. If I gave you a quadratic equation in vertex form, it would look like this. Do you see any number that's kind of like quote unquote missing. That's the three characters. Who's not there? A. What does that do you think mean about our build? It's a normal. It's the default out one, up one, out two, up four, out three, up nine. So there's a one there. A is one, right? But we just generally ignore it if just like we always have. So let's get right to it. So the numbers each have a purpose. What do you think the -4 is going to make us do? Good job. And before you hung out for a long time with a dork like me, you would have been inclined to say left four. That's what a common sense person would say is like, what are you doing? Like, that's a minus. Why don't we go left? But you've seen this theme before about trying to center things out and make them equal zero. This is not the first time we've seen this idea that, like, we've seen it with factors. When we try to make factors solve equations, if it says x plus 3, then we know x is -3. Bless you. If we see x -5, we know that the answer is +5 because we're trying to make the parentheses equal zero. So you would want to add into your notes that the horizontal mover is the backwards one, like it has been before. So the minus does not mean to go left, like our intuition tells us it means to go right. And then what do you think the +1 at the back means to do? Up one. And again, just like it's always been, the inside the parentheses one is the one that's weirdo backwards, and the one that's afterthought is normal, like exactly what our brain tells us it should be. So finding the vertex does not require any sort of mathematical expertise at all. You literally just follow those directions. No negative b over 2a, no plugging stuff back in, no copy dot flop, no nothing. Simple pimple. So we're simply going to leave from the origin, and we're going to go right four and up one, 1, 2, 3, 4, 1, and we're going to place our vertex, and it's that easy. And all you have to do once you get to the vertex is just build. And like I've shown you before, I hate to be this guy, but you don't need any of this anymore. You need only the number A right there, which is 1, right? Nothing else matters once we get to the build site. And so since it's a default build and it's a +1, we're simply going to go and do the normal build. Out 1, up 1. Out 2, up 4. Out 3, up 9. And that is why we inevitably do not struggle with vertex form. Now, do people sometimes still get them backwards? Unfortunately, it happens. But I don't think I'm asking a lot of you there. The one on the inside, remember, is backwards, horizontal. The one on the outside is logical, normal, uppy, downy. And then you just place a build. And then you would, of course, sketch that. I don't want to waste your time by displaying my lackluster artistic skills, but obviously no parabola is complete until you actually sketch the parabola and, put arrowheads on the ends, stuff like that. Do you have any questions about that? So let's just run through a few more examples now that you know the gist. Like I said, if this takes too long, then I just need to figure out what I'm doing wrong. Our next one is y equals -2 times the quantity of x plus 2 squared minus, +4. Getting to the vertex, oof, that's easy. Quick directions. Remember, we never use the word over, so we are tight. We use only the words left, right, up, and down when we discuss directions on a grid. Where do we go? Perfect. That's how easy it is. Left 2, up 1, 2, 3, 4. And then at this point, once you have the build site locked in, you no longer have any use for this portion of the equation. If it's in vertex form, we can throw all that stuff away, and now you just got to go make the build. And what kind of build are we going to do here? Skinny and down. Right. So it's our ×2 build, which we've been practicing. You know the drill. So we're going to go out 1 and down, not 1, but double 1, which is 2. And then when we go out 2, how far down are we actually going to go? 8. Out 2. Normally we go down 4. 1, 2, 3, 4. We go another 4. 1, 2, 3, 4. The builder number, as always, is just there to tell us how to stretch or shrink our ups and downs. And we don't have enough room because if we were to go out 3, How far down would we go? 18. And there's not enough room, on most, I would have to place the vertex a lot higher, but we're out of real estate. You'll run out. If you go down, I think you can go down maybe 14 and then you run out of space and you don't want to, go that far out. So then you make the sketch, graph the parabola. All right, there's two little twists and turns that I want to just address in this lesson, and then I'll shut up because sometimes there are numbers that are missing, like this. And y'all are smart enough that I probably don't even need to say this, but I'm going to put it in here anyway so that we can call this officially complete. And anyone who watches the video would have an example of, I think, every possible contingency. So what's different about this one? It doesn't have a K. It doesn't have a vertical shift. So what does that mean? Yeah, you just go right to and you call it a day. Like sometimes, people with like a lot of math panic in their blood, they say, whoa, 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 this doesn't look like the other ones. And I'm like, then make it look like the other ones. Like if that's something you want to do, then go right ahead. But it's a simple matter of a horizontal shift and nothing else. So we merely follow the right two from inside the parentheses, place our vertex. And what kind of build is this going to be? A fatty. And we know it gets fatter because the fourth is like the man keeping the points down. So I'll zoom in on this. And when we go out one, how far up will we go? 1/4 of the way to what we normally would go. So we estimate that. Just make sure it's obviously lower than a half. When we go out two, how far up will we go? One, because that's 1/4 of what we normally go. And when we go out three, we'd normally go up nine, right? What's 1/4 of nine? Remember, I'm just asking you when I say 1/4 of nine, I'm just saying to you 9 divided by 4. That's what a fourth means. Divide by 4. 2.25 is perfect. So we're going to go out 3 and we're going to go up 1, 2 and a quarter, which is right there. And I won't budge ever at any point in my teaching career on this. You need to graph as many points as whatever graph you're working on will allow. Sometimes, like you saw in the last problem, that was the vertex and 2 more on each side. This one's going to probably have 5 more on each side. I don't know. Let's find out. If we go right 4, how far up will we go? 4. 4, because it's 1/4 of 16, right? So up 1, 2, 3, 4. If we go out 5, how far up will we go? Nice job. And you've seen these numbers before. You almost get to a point where you don't have to keep recalculating them. If you do all the homework and practice enough, you just start to get math facts stuck in your head. 5 would be 25. 1/4 of 25 is 6 and a quarter. So we're going to go up 1, 2, 3, 4, 5, 6 and a quarter. And we ought to have room for one more, I think. It looks like we got the real estate. Let's find out. If we go out 6, how far up will we go? 9, because that's 1/4 of what we would normally do. So we're going to go out 1, 2, 3, 4, 5, 6, and go up 1, 2, 3, 4, 5, 6, 7, 8, 9. And then at that point, it's pretty obvious that we're out of space. So there's our fatty. So the purpose of that example in the note card on the note card today was to just point out so that we don't have to talk about it, that when you don't see a vertical shift, that just means it doesn't have one. It doesn't move up or down. The vertex just stays put. It only goes right or left. And if you're a good listener and you're pretty in tune with where this is headed, you know the last one is going to be missing something else. So what's this one missing? The H, the horizontal shift. And again, we're not going to panic. I mean, if you're a math panic person, then this version of the exact same problem is for you. Is that silly to write? I mean, I think so. But if it helps you and you do you, that's fine. There's no harm there. It just reminds us, though, that we don't move left and we don't move right. Where do we go? Yeah, we simply go up 3. So this is one with only a vertical shift. And what kind of build are we going to do here? Yep, chunky downwards. You got it. So we just have to take the number in front, and that's 1/3. And we build all of our verticals according to that. And again, remember, please, that a third is just divided by 3. So if we go out 1, how far down do we go? A third, right? So that's, again, we don't have to be perfect, but we want it to look like it's less than halfway. We can handle that. You know, could someone mistake that for a fourth? I don't know, maybe, but it certainly would not be mistaken as a half because we deliberately make sure that it's not halfway down to negative 1. If we go out 2, how far down would we go? 1 and a third. And you can use a calculator for these calculations if you're the person that likes to do that. You always just take your normal, which would be 4. We'd go down 4 and you divide it by 3. And if you know math pretty well, you know that that's 1.3-ish, 1 and a third. If you don't, type it in your calculator and it'll tell you the same thing. So that means if we leave the vertex and go out 2, we go down 1 and a third of the way to 2. The next one is nice. If we go out 3, how far down will we go? 3, because that's a third of the normal 9. So 1, 2, 3, 1, 2, 3. And then we're going to have a bunch more tweeners. The next nice one won't be for a little bit here. The next ones are going to be back to the fractional, the annoying values. If we go out 4, that would be 16. But again, since we're doing a third, we just divide by 3. What's 16 divided by 3? How many times does 3 go into 16? 5, with 1/3 left over. So we go down. So we go out 1, 2, 3, 4, down 1, 2, 3, 4, 5, and a third of the way. And we ought to have room for one more, I think. This probably will be the last. No, I think we got maybe room for 2 more. If we go out 5, we would normally go down 25. What's 25 divided by 3? 8, with a third left over. Good job. 3 goes into 25 8 times. So we're going to go out 1, 2, 3, 4, 5, down 1, 2, 3, 4, 5, 6, 7, 8, and a third. And we have one more nice one coming up here, because if we go out 6, we'd normally go 36. But what's 36 divided by 3? 12 is perfect. So we can fit one more. So we're going to go out 1, 2, 3, 4, 5, 6, down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And at that point, obviously, we're out of space. So I learned a long time ago about quadratics that it's best to teach you guys that on the first day I taught you, if all else fails, make a table. If you're taking a test someday and I'm not there to help you and you go, I don't remember what to do, make a table. Make a table and pick some X's, 5, 6, 7, 8 of them, and plug them back into the equation and keep getting Y's. And then you can get a picture of the graph. But that's not the best way to make a graph. The best way is if I can save myself having to do a whole bunch of nonsense. And that's, following the get to the build site and then build it from there method. So Vertex form should be cake. I have an assignment for you. It's on paper. I think it's got like 12 problems or something. I don't know. That should not be an issue. So if you get done with the Vertex form, which you probably will, make sure you wrap up any other assignments that you're not done with. And if you get all that done, then good job. Sound good? All right.